The fundamentals of transport processes. This is lecture number 9, and last time we were discussing unidirectional flows. Just to remind you of where we started, I first explained to you why transport processes are important in material transformations, both physical and chemical. It is not just sufficient to put in the raw materials, put in the heat required, the product need not come out. You need to make sure that the materials get to the place where the transformation actually occurs, and that is where the discussion of transport phenomena is so important. We looked at dimensional analysis and empirical correlations based on dimensional analysis, and I tried to give you some physical insight into what those dimensionless groups mean. And we talked about diffusion, the molecular phenomenon of diffusion, and how that translates into diffusion coefficients, why the values of the diffusion coefficients are the numbers that they are in gases and liquids. And then we got down to the business of solving actual problems in transport phenomena. The simplest configuration you can consider is unidirectional transport. That means that transport occurs only in one direction, and that is why the problem is greatly simplified. In what is called a Cartesian coordinate system, the 3 coordinates are x, y, and z, and unidirectional transport in a Cartesian coordinate system means that the transport is taking place only along one direction. And the simplest example in Cartesian coordinates is the transport between 2 flat plates. And we looked at various instances of heat and mass transfer between 2 flat plates, both at steady state and at unsteady state. So, in the simplest example of heat transfer, you have 2 plates, one of which is at a higher temperature and the other of which is at this is at a lower temperature and this is at a higher temperature. Because of this temperature difference, energy is transported from the higher to the lower temperature, and that results in a temperature gradient. In the final steady state, the temperature gradient is going to be linear. It is going to be a linear function of position. You will have a linear variation in temperature between the 2 plates, which means that the flux is a constant, because flux is proportional to the derivative of the temperature. However, one could also consider unsteady situations. For example, you have this entire system at one constant temperature T naught, and instantaneously you change the temperature of the bottom surface to T1, and the temperature is going to change as a function of time. Okay. It is going to look something like this at very early times, and as time becomes larger and larger, you are going to get a flat profile in the long time limit. Same thing with concentration. You can have 2 plates, one at a lower concentration, one at a higher concentration, and there is going to be a flux from one plate to the other. At steady state, when there is nothing changes in time, that flux has to be a constant and the concentration has to be linear function of position between the 2 plates. We looked at a momentum transport problem. Okay. In this case, one plate is stationary, it has no velocity, the other plate is moving with a constant velocity. In the final steady state, of course, the velocity profile is linear, and the momentum flux or the shear stress is going to be a constant throughout. Okay. But we also want to look at what happens when there is a variation in time. Okay. And that was the purpose why we started looking at what are called shell balances. The idea is as follows. We write a balance equation for a small differential volume within the fluid. We assume that the length, the thickness of this volume as well as the area of this volume is small compared to the macroscopic scale, which in this case is the total length L. It has to be small compared to L, but it has to be large enough that the continuum approximation is valid. In other words, it has to be large enough that it contains a large number of molecules, going back to our earlier discussion of the continuum approximation. If it contains a large number of molecules, then you can define continuum fields. In this case, the energy density field. Okay, so because of the gradient in the difference in temperature, there is going to be energy coming in and going out of this volume. The bottom surface of this volume is hotter than the top surface. Therefore, the flux at the bottom will there will be a flux coming in at the bottom and a flux going out at the top. Energy conservation condition basically said that change in energy within this time delta t is equal to energy in minus energy out. Simple. Okay. Just a balance telling you that there can be no creation or destruction of energy. This is valid only when there is no sources or sinks. If you imagine a chemical reaction which was generating heat, there would be a source. If there was an endothermic reaction which absorbed heat, there would be a sink of energy. If none of these is present, you just have a fluid which neither generates or consumes energy, then the balance condition basically says that change in energy in the time delta t is equal to energy in minus energy out. Okay. And we calculated explicitly the change in energy within a time delta t. The energy within this volume is equal to the specific energy per unit volume at this point x, y, z times the small volume around it. Okay. Therefore, the change in energy was written as E at x, y, z t plus delta t, E at t x, y, z t plus delta t minus E at x, y, z t divided by times the volume itself. Okay. And that we wrote in terms of the specific heat and the temperature here. Okay. The fluxes in and out, okay, is equal to the heat flux. The flux now is in the z direction because there is a variation in temperature only in the z direction. So, the energy in is qz, okay, times delta x times delta y, that is the qz is the flux energy per unit area per unit time. Qz times delta x delta y is the energy in per unit time, which is the flux times the area, and then multiply that by delta t to find out how much is coming in within that time interval delta t. Okay. Put all of these together and we got a balance equation which was basically of this form: rho Cp into dt by dt is equal to minus partial qz by partial z. Okay. So, this basically tells you that the rate of change of specific energy within that volume is equal to the rate at which energy comes in minus the rate at which it is going out, okay, the difference in fluxes across the two surfaces, the bounding surfaces. And then we need an equation for the flux, okay, Fourier's law of heat conduction. Qz is equal to minus k partial t by partial z. Note the partials here, these are important. It implies that you are taking the variation in temperature with z, keeping all other coordinates the same. That is, you are varying z a little bit and finding out the difference in temperature, keeping x, y and t a constant. Okay. And from that we got this diffusion equation for the temperature, where alpha is the thermal diffusivity. Did exactly the same thing for mass. Instead of T we have C, the concentration. Instead of alpha we have D, the diffusion coefficient, and you get the exact same equation. Okay. The exact same equation, except that concentration is substituted for temperature, mass diffusion coefficient is substituted for the thermal diffusion coefficient. In all of these we assume that the diffusion coefficients both for mass and the thermal diffusion coefficients are not functions of position. Okay. If they are functions of position, it gets a little more complicated. We will assume that the fluid properties are uniform, so the thermal conductivity, the mass diffusivity does not depend upon position. The form of the equation for momentum diffusion was slightly different. Okay. It came out of Newton's law, third law of, Newton's laws of motion. Rate of change of momentum in a differential volume is equal to the sum of the applied forces. Okay. And there I had defined for you, okay, in some detail what is the stress tau x z. Okay. It is the force per unit area in the x direction acting at the surface with outward, okay, note outward unit normal in the z direction. Okay. And I also told you that if the outward unit normal is in the minus z direction, the force will be minus tau x z, because if you interchange, if you reverse the direction of the unit normal, the direction of the force also changes according to Newton's third law. Okay. And then we basically use the balance condition that the rate of change of momentum is equal to sum of the applied forces to obtain an equation for momentum transfer, which once again looks identical to the equations for heat and mass transfer, except instead of concentration you have the velocity ux, instead of mass diffusion coefficient you have the kinematic viscosity or momentum diffusivity nu, ratio of viscosity and density. Okay. And we talked a little bit about scaling. Okay. I said that rather than work with these unscaled coordinates alpha, t, ux and c, right, I could define scaled coordinates. Okay. In this case, t star is equal to t minus t naught by t 1 minus t naught. T star is equal to 0 on the top surface and t star is equal to 1 on the bottom surface. If I define z star is equal to z by L, then z star is equal to 1 on the top surface and z star is equal to 0 on the bottom surface. Defined this way, in all cases the concentration, the scaled temperature varies between 0 and 1, the scaled concentration varies between 0 and 1, the scaled velocity varies between 0 and 1. So, the equations are the same, except that one has to put in the appropriate diffusivity. The lengths all scaled vary between 0 and 1. The quantities being transported once again vary between 0 and 1. So, all of them have a common solution. Okay. This is the solution at steady state. Okay. The linear profile for the temperature, concentration and velocity fields. Okay. So, that is where we stopped off in the last lecture. Now, we come to looking at the simplest unsteady state problem. Okay. That is the problem that I just explained to you a little earlier. Okay. If initially the temperature is equal to 0 everywhere and at some time t is equal to 0, the temperature at the bottom surface is increased to 1, then what happens? How can we measure the temperature field in this unsteady situation? That is the topic for today's lecture. So, let us go ahead with analyzing that problem. Okay. So, back to our problem, 2 plates, and I will just work in scaled coordinate. Okay, z star is this axis. I can scale it by the thickness, whatever the thickness is, I can scale it by the thickness to get this boundary at z star is equal to 0 and this boundary at z star equals 1. Okay, so, the scaled distance varies between 0 and 1. Okay. The boundary conditions in this case are as follows. Okay. For t less than 0, right, I will assume that the concentration, the temperature T star is equal to 0 everywhere. Okay, so, it is equal to 0 here, okay, and it is equal to 0 on this surface as well. Okay. And at t is equal to, at t is greater than or equal to 0, T star is equal to 1 at z star is equal to 0. Okay. So, at the initial time instantaneously, so initially if I plotted the temperature was basically equal to 0 everywhere, scale temperature. I showed you in the last class how to scale it. Okay. So, this is the temperature T star is equal to 0. Okay. At the initial time, I instantaneously increase the temperature here to T star is equal to 1. Okay. So, initially the fluid has not felt the heat coming out of this plate. Okay. So, it is just at 0 temperature. Gradually there is going to be a diffusion of heat from the bottom, because I have raised the plate of the raised the temperature of the bottom plate. Okay. So, initially I am going to get a temperature profile that looks like this. That temperature profile will slowly expand as the heat goes further and further up, until in the long time limit I am going to get back a linear temperature profile. Okay. Let me just do that a little more carefully. The long time limit I am going to get this linear temperature profile. Okay. And I want to find out how the temperature evolves from this initial state to the final linear state. Okay. Before we tackle the problem of the temperature evolution from the initial to the final steady state, okay, let us look at the very early instance of time, okay, when the temperature disturbance due to the bottom plate has not yet gone far into the fluid. Okay. So, if the temperature disturbance at the bottom plate generated due to instantaneously increasing the temperature of the bottom plate, if it has not gone very far up, right, then this disturbance is going to be restricted to what is called a penetration depth. Okay, it is going to be restricted to a penetration depth, okay, which is small compared to the total height. Okay. The total height was z is equal to 0 to z is equal to L. Okay. If the penetration depth is small compared to that, that means that the as far as the temperature field is concerned, the top surface is very far away. Okay. So, I do not have to know the exact location of the top surface, I just have to know that as I go further and further up, the temperature reaches 0, okay, as the distance becomes very large. Okay. Okay. So, my problem, rather than T star is equal to 1 at z is equal to 0 and T star is equal to 0 everywhere, okay, if the penetration depth is small, okay, compared to the total height, then I can say that T star is equal to 0 as z goes to infinity. Okay. When I go further and further up, the temperature approaches 0. Okay. So, the temperature in this case is approaching 0, in this case it is approaching 0 as I go further and further up. Okay. So, in that sense I am effectively solving a problem in an infinite domain. Okay. The problem reduces to a problem in an infinite domain, okay, because the penetration depth to which the temperature disturbance due to the bottom surface has been felt is very small compared to the total height. Okay. So, this is the temperature boundary conditions that I will use, okay, and the differential equation for the temperature field that we had got was dt by dt is equal to alpha d square t by dz square. Okay. So, this was the differential equation. When we initially scaled variables, we scaled it by the total height of this the distance between the two plates h. Okay. We scaled it by the total distance between the two plates. Okay. However, now I am considering a situation where the distance to the top plate is large compared to the penetration depth within the flow. So, I am effectively enforcing boundary conditions in the limit as z goes to infinity. Okay. If the penetration depth is small compared to the height, it does not matter what the height is. Okay. It can be h, it can be 2h, as long as the penetration depth is small. The only requirement for the temperature field is that the scale temperature goes to 0 as h goes to as z goes to infinity. Okay. So, previously, because I had a finite depth, I scaled all length scales by h. In the present case, h is no longer a parameter in the problem. Okay. So, how do I scale the distance z? Let us go back and look at all the relevant variables in the problem. Okay. One relevant variable, of course, is the temperature T star, but that is already dimensionless. Okay. T star I had scaled as T minus T naught by T 1 minus T naught, varies between 0 and 1, no units, it is dimensionless. So, that cannot be a dimension that is important in this case. Okay. I have 3 others. two are the coordinates, one is the z coordinate, the other is time. Okay. And the only other thing that I have in the problem is this diffusivity alpha. Okay. So, there is one dimensionless variable t star, two coordinates z and t, and one dimensional parameter, the thermal diffusivity alpha. So, I do not have any length scale to scale z by, okay, because initially I had said that the distance between the plates was h, but then if the temperature field has not penetrated that far, right, it does not matter what h is. Okay, the temperature field near the bottom surface is not going to depend upon what the total height is. Okay. So, that is the issue here. Okay. Now, the answer to this problem is as follows. Okay. I have three variables, okay, t, z, alpha, which have dimensions, okay, and there are only two dimensions that they can depend upon. They do not depend upon mass, okay, they depend only upon length and time. Okay. Therefore, from these three coordinates I can get only one dimensionless group. Okay. I told you last class that we tried to scale all variables when we try to solve this problem. Okay. So, if I did the problem simplistically, what I would do is to scale z by a height and t by a time. Okay. In this case, I do not have a height, okay, because the penetration depth is small. So, the boundary condition is applied at z going to infinity. I do not have a scale for time either. Okay. Out of these three, I can get only one dimensionless group, okay, and that dimensionless group is a similarity variable. Okay, that dimensionless group is a similarity variable, okay, z by root alpha t. Okay. So, just from dimensional analysis, okay, if the penetration depth is small, so that I am applying a boundary condition at infinity, the progression of the temperature field with z and with time are linked, okay, and they are linked in such a way that the progression depends only upon this similarity variable. Okay, or similarity coordinate, okay, and that effectively reduces the problem from two independent variables z and t to just one independent variables, which is a dimensionless necessity. I am sorry, which is a dimensional necessity, okay, because there are no other dimensionless groups that I can form in the problem. Okay. So, if the temperature field depends only upon this dimensionless similarity variable, then I should be able to express my entire equation in terms of that dimensionless similarity variable alone. Okay. So, what I need to do is to express the derivative with respect to z in terms of the derivative with respect to psi. The derivative with respect to t also can be expressed in terms of the derivative with respect to psi. Okay. Put that into this equation, and if my premise is correct that it depends only through this variable psi and not individually through t, z and alpha, the final equation that I get should not contain any of these parameters t, z or alpha. It should be only a function of psi alone. Okay. So, that is the basic idea. Okay. So, let us proceed with the solution. Okay. So, I have my equation partial t star by partial t is equal to alpha partial square t star by partial z square. Okay. And I have defined my similarity variable psi is equal to z by square root of alpha t. Okay. This is dimensionless because z has dimensions of length, alpha is length square per unit time. So, therefore, alpha t has dimensions of length square, and therefore, z by root alpha t is dimensionless. Okay. So, the derivative with respect to time partial t star by partial t is equal to partial psi. Okay. Chain rule for differentiation. Okay. Partial psi by partial t is equal to minus z by 2 root alpha t power 3 halves, okay, times partial t star by partial psi. Okay. Now, z by root alpha t is psi itself. Okay. Z by root alpha t is psi itself. Therefore, I can also write this as minus psi by 2 t partial t star by partial psi, okay, using chain rule for differentiation. Okay. On the right hand side, okay, partial t by partial z, okay. First take the derivative with respect to z and then with respect to psi by chain rule. Okay. This is 1 over root alpha t partial t by partial psi. Okay. The second derivative, partial by partial z of partial t by partial z, okay, is equal to partial psi by partial z, okay, partial by partial psi of, okay, and this is equal to 1 by alpha t partial square t by partial psi square. Okay. So, now I have to substitute this into the original diffusion equation. Okay. Therefore, I will get partial, rub it out. Okay. I will get minus psi by 2 t partial t by partial psi. Okay. This is equal to alpha by alpha t partial square t by partial psi square. Okay. And I can cancel, I should be careful here. Okay. And you can cancel out, okay, alpha there and t here to get an equation of the form minus psi by 2 partial t by partial psi is equal to partial square t by partial psi square. Okay. Good. So, just to recall, okay, I had previously said that since by dimensional analysis there is only one dimensionless group which involves both the z coordinate and time, okay, I should be able to define this entire, I should be able to rewrite this entire equation in terms of this dimensionless group alone. Okay. Once I have written it that way, the equation should not contain individually z, t and alpha, it should only contain this dimensionless variable psi. Okay. And I do find indeed that the final equation that I get does contain only this dimensionless variable psi. Okay. But however, if I am to solve this equation, I need boundary conditions. Okay. What are the boundary conditions that we had? Okay. Okay. At z is equal to 0, okay, T star is equal to 1. Okay. So, at the bottom plate, the temperature T star is equal to 1, at z is equal to 0. Okay. So, that, okay, z is equal to 0 is equivalent to psi equal to 0, okay, because psi is equal to z by square root of alpha t. Okay. The other boundary condition was that in the limit as z became large, okay, z going to infinity, t star was equal to 0. Okay, the limit as z goes to infinity, t star was equal to 0. Okay. Z going to infinity is equivalent to psi going to infinity. Okay, psi going to infinity because z psi is equal to z by square root of alpha t. Okay. There was a third boundary condition, rather an initial condition. okay, and that was that at t is equal to 0, okay, at the initial time, okay, when I just switched on this temperature field at the bottom, everywhere else within the flow, within the fluid, the temperature was equal to 0. Okay. At the initial time t is equal to 0, when I just switched on the heating from the bottom, the temperature was equal to 0 everywhere else, okay, apart from that bottom plate. Okay. So, that would imply that at t is equal to 0 for z greater than 0, t star is equal to 0, right. At time t is equal to 0, everywhere in the fluid apart from that bottom plate, apart from z is equal to 0, the temperature is equal to 0. Okay. T is equal to 0, psi is equal to z by square root of alpha t. Okay. So, this implies that this has to be applied at psi going to infinity. Okay. And you can see that when expressed in terms of the psi coordinate, these two boundary conditions are exactly the same. Okay. I had started off with a second order differential equation in the z coordinate, a first order differential equation in time that required two boundary conditions in the spatial coordinates, one initial condition in time, and then I reduced the variables using the similarity transform to an equation just in terms of one variable psi. Okay. This equation was only in terms of the variable psi, okay, and because it is a second order equation in psi, you can have only two boundary conditions for this equation. Okay. And therefore, what we find is that one of the boundary conditions and one initial condition of the original problem turn out to be exactly the same when re-expressed in terms of psi, so that we get a consistent solution. Okay. The other thing that I have done here is to convert a partial differential equation with variations in time as well as z into an ordinary differential equation. Okay. And that is the big advantage of this method. The similarity solution was defined so that the partial differential equation which I originally had is in transformed coordinates an ordinary differential equation, and an ordinary differential equation is simpler to solve. Okay. It is a linear ordinary differential equation, and so I can solve it to get a solution for the temperature profile. Okay. So, my equation is minus psi by 2 dt star by d psi is equal to d square t star by d psi square. Okay. So, I can solve this now. Okay. So, if I define u is equal to dt star by d psi, then I will get minus psi by 2 u is equal to du by d psi, okay, and u is equal to a constant e power minus psi square by 4, okay, and this is equal to dt by d psi. Okay. Therefore, t is equal to c integral, okay, 0 to psi d psi prime e power minus psi prime square by 4, okay, plus some other constant d. Okay. And I have boundary conditions t star is equal to 0 as psi goes to infinity, okay, t star is equal to 1 at psi is equal to 0. Okay. Using this, I can easily determine the two constants. Okay. Using these two boundary conditions, I can determine the two constants in the equation. Okay. So, this will give me t star is equal to 1 minus integral 0 to psi d psi prime e power minus psi prime square by 4, okay, divided by integral 0 to infinity prime square by 4. Okay. That is what I would get after I enforce both boundary conditions. Okay. And I put in the solution, the similarity transform once again. Okay. That similarity transform, you will note, comes in only in the limits of this integration. Okay. Therefore, in terms of the original variables, okay, I can write T star is equal to 1 minus integral 0 to z by root alpha t, okay, d psi prime e power minus psi prime square by 4 by integral 0 to infinity d psi prime. Okay. So, that is the final solution for the temperature field. Okay. The temperature field depends on position and time only through this scaled coordinate. Okay. And now, we are in a position to answer the question that we had originally asked, what is the penetration depth? Okay. Clearly, the temperature as z by root alpha t becomes larger and larger, in the limit as it becomes large, it goes to infinity, the temperature will go to 0. Okay. The temperature deviates significantly from 0 only when z by root alpha t, okay, is approximately 1, okay, is of order 1. Okay. If it becomes large, there is virtually no deviation from 0. Okay. Therefore, the penetration depth in this case is proportional to square root of alpha times t. Okay. Okay. It goes as square root of alpha times t. Okay. So, the penetration depth is increasing as square root of t as time increases. Okay. The next question, what did we mean initially when we said that the time is small enough that the penetration depth is small compared to the total height? Okay. Penetration depth is small compared to the total height only when square root of alpha t is small compared to the height h, okay, or when t is small compared to h square by alpha. Okay. So, this is the time period over which we can use a similarity solution, when the transport problem looks like the transport into an infinite fluid, because the height is large compared to the penetration depth. Okay. So, this gives me the temperature profile at every instant in time. A second relevant question that one can ask is, for example, what is the heat flux at the bottom surface? Okay. The heat flux Q is equal to minus K times dt by dz, okay, where K is the thermal conductivity. Okay. Expressed in terms of the scaled temperature, this will be equal to minus K into T1 minus T naught into partial T star by partial z, okay, because T star is T minus T naught by T1 minus T naught. Therefore, dt star by dz is dt dz divided by T1 minus T naught. Okay. Good. Now, this we have to express in terms of the scaled variable psi. Okay. So, this when expressed in terms of the scaled variable psi becomes T naught into dz d psi by dz times dt star by d psi. Okay. And d psi by dz is 1 over square root of alpha t. Okay. So, this is equal to minus k into T1 minus T naught by square root of alpha t, okay, into dt star by d psi. Okay. The flux at the bottom, okay, heat flux at z is equal to 0. Okay. Z is equal to 0 also corresponds to psi is equal to 0, because psi is equal to z by square root of alpha t. Okay. So, Qz at z is equal to 0 is equal to minus k into T1 minus T naught by root alpha t, okay, into dt by d psi at psi is equal to 0. Okay. And now you can use this solution for t in order to find out what is dt by d psi. Okay. Clearly, here this constant is 1 over integral 0 to infinity of d psi prime. Okay. So if I use this solution, the derivative with respect to psi will just remove this integral sign on the second term and you substitute psi is equal to 1 here. Okay. So this is equal to minus k into t1 minus t naught by square root of alpha t, okay, into minus 1 by integral 0 to infinity d psi prime e power minus psi prime square by 4. Okay. So this basically is equal to k into t naught minus t infinity by root alpha t integral 0 to infinity d psi prime e power minus psi prime square by 4. Okay. So this term here, this is just a constant, it is a definite integral from 0 to infinity. Okay. So I am getting the heat flux decreasing with time as 1 over square root of t. Okay. The penetration depth increases, the heat flux is the gradient of the temperature. It will go approximately as the temperature divided by the penetration depth. As the penetration depth increases, the heat flux decreases as 1 over square root of t in this particular problem. Okay. So to recall, we used similarity transform because there were no length or time scales in the problem with which we could scale length and time by. Okay. And because of that, we managed to get a solution which was only in terms of a similarity variable. Okay. Now, the similarity transform can also be applied for mass and momentum transport equations problems. Okay. The only thing is that I would substitute the mass diffusivity for the thermal diffusivity here in my similarity variable. I would substitute the momentum diffusivity, kinematic viscosity nu for the thermal diffusivity here in this problem. Okay. So, for example, okay, if I considered a mass diffusion problem where there was diffusion from a surface, C star is equal to 0 here and C star is equal to 1 here, okay, and initially C star was 0 everywhere, okay, and then I considered the problem of early times. Okay, you start off initially with this profile, then you had a profile like this where the penetration depth, okay, was small compared to the total height. Right. It's exactly the same equation, and I can write down the solution C star, okay, is equal to 1 minus integral 0 to z by root d t d psi prime e power minus psi prime square by 4 by integral 0 to infinity. Okay. So, in this case the concentration was 0 everywhere. At the initial time t is equal to 0, I set the concentration of the bottom plate alone equal to 1 and then watch the diffusion from there. Okay. Equivalent momentum transport problem. Okay. Okay. So, I have ux is equal to 0 everywhere. Okay. At time t equal to 0, I set this velocity into motion with a velocity u. Okay, so that ux star, which is the scaled velocity, is equal to 1. Okay. In the final state, of course, I will have a linear velocity profile, okay. But in the very initial stages, the momentum transfer will be limited to a thin region near the base, okay, where the penetration depth is small compared to the total height h. So, in this case I can also write down quite easily what the solution for the velocity is going to be equal to. Okay. Square root of z by root nu T, where nu is the kinematic viscosity. Okay. So, you get exactly the same solutions. These are semi infinite domains where you have one surface and an infinite fluid on top, okay, and either the concentration, temperature or the velocity of the bottom surface is instantaneously changed, and then you find the diffusion going upwards. Okay. So, we do that by the similarity transform. In this case, it was a dimensional necessity. Okay. The fact that there is only one dimensionless group was a dimensional necessity. Okay. However, the similarity transform is more general than that. Okay. We will use it later on when we do boundary layer theory. Okay. We will repeatedly use similarity transforms to reduce the equation from a partial differential equation to an ordinary differential equation. Okay. And I can show you one example here where such a thing is done. Okay. We will consider here the simplest example where we can use a similarity transform not based upon dimensional analysis, but rather based upon physical understanding. Okay. And that is the mass transfer to a falling film of fluid. Okay. Let us say that I have a film of fluid falling downwards, okay, along the wall of some contactor, and there is gas here, there is gas at the surface. Okay. So, at the entrance, okay, so okay, there is an entrance towards the fluid, and then it falls as a thin film along the wall, okay, and it comes into contact with gas, okay, along the wall, and the idea is to dissolve this gas into this film of fluid. Okay. Now, the film of fluid in general will have some velocity profile like this. Okay. We will assume that this width of this film is h, and the total length L, okay, that it travels is now L. Okay. And there is this velocity profile very close to the surface. Okay. Now, clearly, as the gas in the film at the entrance, the concentration of the solute that is being absorbed from the gas, C will be equal to 0 at the entrance. As the solution proceeds, the concentration increases as you go downwards. Okay. At the interface itself, the concentration is a constant value. Okay. It is equal to the equilibrium concentration, okay, the solubility Cs that is in equilibrium with the gas at its particular temperature, pressure and concentration. Okay. So, we put a coordinate system here as usual. Okay. I will take the depth here as z, depth inwards into the film, and the streamwise flow direction as x. Okay. And now, I want to find out what is the concentration in the liquid, okay, as a function of time. My final objective is to get a Nusselt number correlation for this, okay, a correlation similar to the correlations that we had discussed when we did dimensional analysis. Can we get a correlation for this as a function of L, the total length, h, okay, the fluid velocity and the diffusivities. Okay. So, that will be the final objective. Okay. This is now not an unsteady problem, okay, it is a steady state problem. However, the concentration is now changing as a function of x. Okay. So, transport in this case is no longer unidirectional. Okay. There is a variation of concentration in the z coordinate, there is also a variation of concentration in the x coordinate. The reason that I am doing it at this stage where we are discussing unidirectional flows will become apparent a little later on. Okay. Turns out that the solution for this configuration is exactly the same that you get for an unsteady flow into an infinite fluid. Okay. Now, as the gas comes in contact, you would expect that initially the concentration is 0 in the fluid. As it comes into contact, there will be a thin layer of fluid at the surface where the effect of this dissolution of the gas at the interface is felt. Okay. This is the equivalent of the penetration depth in our previous case. In that case, the penetration depth increases with time. Okay. As time progresses, the solute at the bottom dissolves further and further into the liquid. In this case, it is as a function of the x coordinate. Okay, as time increases, the gas at the interface dissolves further and further into the liquid that is trying to dissolve the gas. Okay. Now, so I have two coordinates here, z and x, okay, and I have a velocity field. Okay. I am going to make an assumption, and that is that this velocity is a constant, okay, as far as the flow is concerned. Okay, I am going to make an assumption that u is equal to a constant. Okay. This is an assumption. This is valid if and only if the depth to which the concentration has penetrated is small compared to the total height h. Okay. In other words, I require that the change in velocity between these two positions, okay, has got to be small compared to the magnitude of the velocity itself. Okay. So, if I expand out this region alone, okay, I have this interface, I have this penetration depth here, okay, and then I have a velocity profile along this. Okay, I have a velocity profile that goes like that. My constant velocity approximation is valid only if the change in velocity in this region is small compared to the total velocity itself. If the change in velocity is small, I can assume that the velocity is approximately a constant over the thickness over which there is penetration of the gas. Similar to our assumption in the previous case, okay, that the penetration depth is small compared to the total height. I have to come back and justify this. Okay. So, the balance equations are the same as before, except that now we have a system which is at steady state, nothing is changing in time, but there is a change in the x direction. Okay. So, I will take a differential volume. Okay. This is delta z, okay, perpendicular to the film. Okay. Delta x is along the flow direction. Okay. A second assumption that we will make, we will neglect diffusion along the x direction. There is flow along the x direction, but we will assume that there is no diffusion. Okay. That is assumption number 2, and we will come back and look at under what conditions that assumption is valid. Okay. For the moment, we will assume that there is only diffusion only in the z direction, and there is convective transport. Because the fluid is flowing downwards, there is going to be convection, okay, in the x direction. Okay. And a balance between this convection and diffusion is what is going to give me my differential equation by the shell balance procedure. Okay. So, this is the problem. Okay. I will do the shell balance in the next lecture and then solve it and get a solution for this, and hopefully from that we will get our first correlation between the Nusselt number and all of the other parameters in the problem. Okay. So, we will see that in the next class. I will briefly review before we leave what we did in the present class. Okay. The solution procedure that we used was what is called the similarity solution. Okay. That similarity solution, in this case, it works only when there are no length or time scales in the problem. Okay. I had an unsteady problem. Okay. At z is equal to 0, I had a boundary condition, and I had another boundary condition as z goes to infinity, and an initial condition at t equal to 0. There were no length or time scales in this problem. Okay. And therefore, when I posed my differential equation, I had a deficit of dimensions to scale my variables with. There was no length scale, z going to infinity, no length scale in the problem, nothing to scale z with. Okay. There was no inherent time scale in the problem. The only thing that I had in the problem was the diffusivity alpha. Okay. And from the diffusivity alpha and the z and t, I could get only one dimensionless group. Okay. So, this implied that just based upon dimensional analysis, there is only one independent dimensionless variable which involves both z and t. Okay. And that was related as follows. If this is true, then my entire differential equation I should be able to express in terms of psi alone. The differential equation cannot depend independently on alpha and z and t. It should depend upon psi alone. Okay. And that is what I got. I got a final equation here which depends only upon psi alone and not individually on z and t. Not sufficient for the equations to be reduced to just an equation for psi. You should be able to reduce the boundary conditions as well. Okay. And the original problem had two boundary conditions, one initial condition. Okay. The problem in terms of the similarity variable should have only two conditions because it is a second order differential equation in psi alone. And I showed you that one boundary condition and one initial condition, when expressed in terms of psi, reduced to the same condition. Once that was done, then I had a way to solve the problem. Okay. And from that we found that the penetration depth is increasing as square root of alpha times t. Okay. And obviously, if you had a finite channel, the analysis that we did will be valid only when t is small compared to h square by alpha. Okay. At these very initial times, this analysis will be valid. When t becomes comparable to h square by alpha, then the influence of the boundary condition of the top plate is felt, and this analysis is no longer valid. Okay. And I showed you what the solution was, and the heat flux decreases at t power minus half. And I told you that you can get exactly the same solutions for heat and mass for mass and momentum transfer. I have set up this problem for you. We will continue this in the next class and try to get a correlation for the Nusselt number. We will see you in the next lecture.